Okay, Chemistry Videos, Electron Configuration. Now, electron configuration is basically just the address of an electron, of all the electrons within inside that particular element, okay? Electrons fill around the nucleus of an atom following very specific rules. There are three basic, there's a couple more, but three basic ones. There's a scientist by the name of Aufbau, one by the name of Hund, and Pauli. They did a lot of studying on this, and that's why they have their principles and their rules and stuff of that nature. Now, I've not seen in several years them specifically ask you these scientists' principle, but you need to understand the concepts of it. As electrons fill up around the nucleus of an atom, because remember, atoms, originally were created in the Big Bang, and then as each one goes through, supernovas, stars, and things like that, because our sun is filled with nothing but hydrogen, and at its core is filled with helium. So it is burning hydrogen, crashing those nucleuses of those hydrogen atoms together and creating helium, which then is more dense and goes to the center of the star. As a star goes into a supernova and explodes, then there's enough power to create larger and larger elements, and that's how all the elements are there. So we get these nucleuses, and inside here is a number of protons, which are charged. Okay? There's also neutrons inside there, and we'll talk about those in a different deal, but there is no charge on there. So the electrons then will fill up in energy levels. Now, when you look at a periodic table, that energy level is the row number. Row 1, row 2, row 3, that's how many energy levels there are. And electrons, according to Aufbau, okay, that's the row number, okay, electrons are only going to fill up depending on its energy level. So when an electron comes down from wherever it came from, a star or wherever out there, because they're all floating around out there in the universe, actually not floating because they're all moving at the speed of light. When an electron then is attracted to this nucleus, it will only fill a hole depending on its level and the level of energy needed to be in that specific row number. So if it's way out away, and we're going to say that this one has, 1, 2, 3, 4 energy levels, and it's in the fourth row in a periodic table, and this electron out here, this electron's going to have a whole higher level of energy than this electron down here in the first row. Hund basically just says that when we're filling in an orbital, which we'll talk about here when I show a periodic table, when we fill in an orbital, I can never have two electrons in the same orbital until all the orbitals are filled, and we'll talk about that here in a second. Pauli says that two electrons will never be the same. So if there's two electrons in this energy level here, and there's orbitals within this energy level, if there's two electrons, one of them is going to have a positive spin and one of them is going to have a negative spin. They will spin in opposite directions. You can never have two electrons with the same energy, the same vibration, the same spin in the same orbital. Now let's get this down into a little bit easier language of what you're going to need for a test. Okay? So basically we have Bohr's, when they say Bohr's atomic model, you have a nucleus, and then you have energy levels. And like we just talked about, these energy levels are like the rows on the periodic table. So if this element here had 3 rows, energy levels, then this would be a third row element, okay? Now, one of the things that we know that we have in the third row is going to be, let's just look at sodium. So sodium has 2 plus 8 is 10. It has 11 protons. So there's going to be 11 protons in the center here. Now, the first row, row 1, can never have more than 2 electrons in it. That's the max. One of them will have a plus spin, one of them will have a negative spin, okay? Then the next row can have 8 electrons in it. And we'll talk about the suborbitals here in a minute, okay? But this is what we're talking about when we talk about a Bohr atom looking at this, okay? Let's get into a little detail here by actually looking at a periodic table. The periodic table is broken down into blocks or sublevels, if you will. We have the sublevel of the S block, which is columns 1 and 2. And those would be the S electrons, okay? Then over here we have the P electrons, the P block. And as you can see, there are 1, 2, 3, 4, 5, 6. There are 6 possible P electrons. The most I can have in the S block are 2 electrons. Now, the D block, okay? The D block never resides, nor this one down here, which is called the F block. These 2 blocks never reside, never will be found in the outer energy level. Because what's the outer energy level called? The very outer shell of any atom is called its valence shell. Okay? Those are the electrons that we're dealing with in bonding, okay? But the D and the F's are never here. The D block elements, you just go D minus 1. So whatever row you're looking for, okay? Say I'm looking for something here like iron, which we will be here in a minute, and I was to find the address and count every one of these electrons across here, okay? When I got to the D's, I would have to go row number, and which it would be 4 minus 1. So those would be 3 D electrons. The F's are the row number minus 2. And the F's never start until you have an element that's either in 6 or row 7. Okay? The D's never start until row 4. And I can have D's in row 5. Okay? So let's look at aluminum here. And we're going to write what's called the complete electron address, which means I got to go across the entire periodic table, and I'm going to count every one of these electrons, okay, and write down their address. And I'm going to go all the way over here to aluminum. So the complete state would mean I'd go row 1. The only thing I can have in row 1 are S electrons, and I have 2 of them. Then I go to row 2, because I got to get over here to aluminum. I go to row 2, I have my S block, and there can be 2. And then I have all of these P's over here, so that's row 2, P block, and there's 6 of those. Then I come down to row 3. So I'm at row 3. I have my 2 S's. And I come over here and I have 1 P. 3 P 1. Okay? Now this is what's called the complete electron configuration, and that is every electron that is in the element of aluminum and how many electrons I have there. Now, in chemistry, because we're kind of lazy, we usually use the abbreviated. So unless they specifically ask you for the complete electron configuration, you're always going to give them this abbreviated, which is also known as the noble gas notation. Because if we take a look here and we say, okay, well, what does that mean? If I look at this chunk right here, that would be 1s2, 2s2, 2p6. That means I am the noble gas of neon. This is the same thing as writing neon. So then I would just write, okay, I don't want to write all that other stuff, I'm lazy. So we're going to have all the electrons of neon, and then it's 3s2, 3p1. And that would be for aluminum. Okay? Aluminum as an element with no charge because it has the same number of protons as it does neutrons. Now, the other thing you have to do is be able to write aluminum if it says it's in excited state. So when aluminum becomes an ion, it loses 3 electrons and becomes a 3 plus charge because it's in this column over here, and that's what we know from studying, electron configuration and periodic table, that most of the elements over here in this one, all of the ones in row 1 form 1 plus, column 2 form 2 plus, and column 3 form 3 plus until we get down here and then things change. But aluminum is a 3 plus. So to do that, I have to be able to write the electron configuration of aluminum in its excited or ion state. So that means I had to lose 3 electrons. Well, shucks, look at this. There's 1 electron here and 2 here, and those are in that outer row, that valence shell. That's usually where we're going to lose it. So I could write this as just being neon, or I could write it as aluminum 3 plus equals a 1s2, 2s2, 2p6. Either one of those would be aluminum as long as I signified that I was in the excited state. Now let's take a look and do another one here for iron. Okay? Now iron's going to sit right here, which means I'm a 4th row element. So I'm going to write iron in its neutral charge, and I'm going to say that that's a 1s2, 2s2, 2p6, 3s2, 3p6. Now I've got my 4th row, 4s2, and then I come over here and I say, well, what are we talking about here? I don't have any p's. No, but this is the D block, and it's in the D block. And remember, the D block is the row number minus 1. So since I'm in row 4, minus 1 would be 3. So I have 3, and there are 1, 2, 3, 4, 5, 6 of them. That's 3D6. And that would be how I would write the complete electron configuration for iron in its natural, normal state. Now, if I was going to write the noble gas notation, I would go to where's my element, right here, row 4. What's the noble gas right in front of it? Argon. And I would say, okay, I'm going to write argon 4s2 3d6. Okay? Now, iron, being since it's a transition metal here, everything in the D block usually can have multiple charges. There are 2 charges that iron has. Iron can either be charged at 2 plus, or iron can be at a charge of 3 plus. So, if I was going to write iron in its 2 plus ionization form, I would write argon, and I would get rid of 2 electrons. The highest energy electrons, as we can see here, if there were p's, it would be p's. These have more energy out here than the s's. Okay, these are out there in those outer shells. Then when we get down closer, they're not as high energy. So I would want to get rid of 2 electrons because that's my charge. So I'm going to get rid of these right here because that's going to be the higher energy. So I'd write argon 3d6. Then if I have my iron at a 3 plus charge, I got to get rid of another electron. Now I've gotten rid of all my s's. I have no p's, so now I got to start getting rid of some of these, and this would be written as argon 3d5. And we would work in that direction. Now let's look at one that does not lose but gain electron. So here we're going to look at iodine. So I got iodine down here, and it is a nonmetal, and nonmetals gain electrons, okay? So we need to we'll write the complete one up here. And after a while, you won't see me in class writing the complete one because it's a waste of time. Because what I would do is I would go to row 5 and I would say, okay, krypton, and I would write the noble gas deal for krypton, and then the element, the electrons, the address of row 5. But we'll write the complete one for you, just so you can get used to it. So that's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now I've got all of these D's here, so that's going to be 3d10, because remember I take row number minus 1, then I got 4p6, now I'm getting into the row that I'm at. I've got 5s2, I've got all of these guys here, so there's another one. 5 minus 1 is 4, 4d10. And then I've got 5p, 1, 2, 3, 4, 5. 5p5. And that would be the complete electron address for iodine. Okay? And then if I was to create the noble gas, I wouldn't have to write all of this. I would just write krypton, 5s2, 4d10, 5p5. Then we're going to write iodine. Iodine only has one charge. It forms a -1 charge. That means it had to gain an electron. So iodine, in its ionized form of +1, has to gain an electron. Well, as you can see over here, in this p area, I've got one electron that I could add. That's why everything in this column forms a plus or a -1 charge. It gains an electron to fill this shell out here so it can be more stable and be happy. So this would be iodine, would be krypton, 5s2, 4d10, 5p6. And that would be writing iodine in its ionized form, its excited state. Okay? That's what we're talking about there. Now the best way to, do this is, like I said, it's just practice, practice, practice. And once you get the hang, it's not that big a deal. But you need to practice as often as you have to until you can create both the complete, the abbreviated, noble gas notation for any element, and also in an excited state. Okay, because this is the one they're going to ask you for in AP Chemistry, okay? The excited state and the regular state. If you have any questions, also remember to always bring your questions into class, because if you don't ask me, I can't help you with your misunderstandings. Remember, as always, chem is try, 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 and never give up.